8A. Simplifying problems. Newton's laws are fundamental to mechanics. By applying them systematically, you can solve almost any mechanical problem. But suppose you have a complex problem involving several interacting bodies. How do you apply Newton's laws to such a problem? 8.1 Free body diagrams. The first step in simplifying a complex problem is to isolate each body and consider it as a separate system. For example, Figure 8-2 is a real-world diagram showing 3 blocks connected by strings. A physics student is pulling upward on the string attached to block 1. To find the net force on block 1, draw a free body diagram of that block. That is, isolate block 1 as the system of interest and determine all the external forces that act directly on the system. What forces act directly on block 1? Gravity pulls down on the block. You can see that the hand does not act directly on the block, but on the string, which then exerts the force on the block. Similarly, blocks 2 and 8 do not pull directly on block 1, but the string tied to the bottom of block exerts a downward force on it. The forces of the strings on the block are called tension, T, forces because the strings pull on the block. These 3 forces, the force of the upper string, T1, the force of the lower string, T2, and the force of gravity, the block's weight, Fw-, are the only forces that act directly on block 1. Figure 8.3 shows the free body vector diagram of block 1. Keep in mind that a string connecting 2 objects exerts the same tension on both objects, but in different directions. 8.2 Transmitting forces in a line, ideal strings. The strings attached to objects in this chapter are ideal strings. Physicists use the concept of the ideal string when studying multiple body systems where the objects are not touching but are connected. Ideal strings have the following properties. They have no mass. Therefore, they do not affect the acceleration of the system of objects. They do not stretch when exerting a force. They exert only pulling forces, not pushes. A pushing force would crumple the string. Forces are exerted only in line with the string. Real strings and ropes approximate ideal strings as long as tension forces are limited to avoid stretching or breaking. For example, the force T1 on block 1 in Figure 8-3 has the same magnitude and direction as the force of the hand on the string. As long as the pull is continuous, an ideal string also holds objects at fixed distances. Therefore, all the objects connected by a string and pulled will have the same speed and acceleration. Although real strings have mass and do stretch somewhat, the mass and stretch are usually small enough to be ignored. So the assumption that a string is ideal is unlikely to introduce noticeable error into your calculations. You can assume that all strings are ideal unless otherwise stated. 8.3 Systems of connected objects. There are many approaches to analyzing the dynamics of a system of objects. If all the masses are known, it is generally easier to determine the motion of the system as a whole first, and then analyze the forces on the individual objects. You need to identify what information is given in order to determine the approach to solving the problem. There is no cookbook method for solving mechanics problems. Using free body diagrams, you can modify the problem-solving method you learned in Chapter 2 to fit problems in mechanics. Most of the changes are additions to Step 1, where it was suggested that you sketch the problem. To apply Newton's laws, you should first draw a diagram of the entire arrangement. This is called the world diagram. Include in this diagram all connections, such as ideal strings, and an arrow showing the direction of motion if that is given. When you have drawn the overall arrangement, you may have to draw one or more free body vector diagrams. Then select a coordinate system for each object. This does not necessarily have to be the same for all objects, especially if they are moving in different directions. After you have drawn free body diagrams, you can continue with the problem-solving method, applying Newton's laws to each diagram separately. When you have reached a solution, check it to see if it is reasonable. It should have the proper units and should agree with any given information. For example, if you find that the individual accelerations for 2 objects connected by a string are either of different magnitudes or in opposite directions, Then you know that you have made a mistake.